In this video, we will be learning about currents, the magnetic field they produce, how that affects magnetic flux, and all these variables interacting with each other. So to start off, we're going to learn about Ohm's law, which states that the current through a conductor between 2 points is directly proportional to the voltage across 2 points. In other words, the current I is equal to voltage over resistance, where the current is measured in amps, denoted by capital A. Voltage measured in volts, denoted by capital V. And resistance measured in ohms, denoted by a half circle symbol. So usually when we see a circuit, it'll be drawn like this. And these two lines right here are representing the battery. The top one we know is the positive side because it's the longer side, and the bottom one's the negative side because it's shorter. When current flows through the circuit, it goes from positive to negative. So it'll go this way and it'll loop around. Here we see resistors. These work to slow down or take away from the current. So the more resistors you have, or the bigger the resistance, the less current. So an important relationship to understand between the variables is that as current increases, the voltage will increase, right? Because the voltage is what creates that current, what helps push that current through the wire. But the larger resistance, the larger restriction, or the less restriction, less resistance, would also compensate for this. However, if your current was decreasing, your voltage would also be smaller, but your resistance may be higher. These are important relationships to understand. So when we look at a roller coaster, we can think of the track. If we look at the track, we can make an analogy to a circuit by saying that the track is analogous to the wire. We can look at the people as the current, because current itself is a bunch of tiny charged particles all moving in the same direction. So we can think of each person as an individual charged particle. Now remember earlier I said the voltage is what creates the current, is what pushes the current through the wire. So we can think of, in our analogy, that the cart carrying the people on the track is analogous to the voltage carrying pushing the current through the wire. And if you've ever been on a roller coaster, you know that after a steep drop, your cart may brake or slow down at certain points on the track. We can call those the resistors, or make them analogous to the resistors. So when you're watching a roller coaster, say person 1 is standing here watching the roller coaster and person 2 over here. Once this roller coaster drops, person 1 will feel a gust of wind, but person 2 will not. So person 1, it's because person 1 is within that certain area to be able to feel that wind. The area that you have to be standing close enough to a roller coaster to feel the wind as it rushes by is analogous to a magnetic field. A magnetic field is a region around a magnetic material, in this case either the wire in the circuit or the track, or moving electric charge within which the force of magnetism acts. So how close do you have to be to the roller coaster to feel the attraction? How close do you have to be, or to feel the wind? How close do you have to be towards the circuit to feel its magnetism? The term for that is magnetic field. Now, magnetic field can be used interchangeably with the term B field. So it's more commonly referred to as the B field. And it is measured in Teslas, denoted by capital T, as we see here. Now, when you're drawing out the B field, it will either be with X's or O's. X's mean that the B field is going into the page, and O's or dots mean the B field's coming out, because remember, B field's an area, it's not a plane. So you can think of into as behind the page, the area behind the page, and out of the area in front of the page. So when we look at our circuit over here, if we were to give it a B field, this means that the B field is going into the page. So a trick to learn how to correlate the direction of the B field and the current in relationship to each other, as well as the overall force, is to use the right-hand rule as we see here. So your fingertips represent the B field going into the page, your thumb represents the current, and your palm represents the force. So if we apply that to our circuit over here, remember earlier the longer side's the positive side, the short side's the negative side, so we decided that the current would be running this way. So if we were to look at just the left side of the circuit where we see the battery with the two lines, your fingertips should be pointing at the screen, and your thumb should be pointing upward, because on the left-hand side, the current's always traveling up. Therefore, your palm is facing left, so the force is to the left. If you follow the current and rotate your thumb with the current at the top, your B field is still into the page. Your thumb should be now pointing to the right because the current has now changed direction. Therefore, your palm is facing up, so we know that the force is up. If we keep following the current with our thumb, we will find that the force constantly changes directions with the current. Now, as you can see, all of these cancel out. So in this specific circuit, there's no net force because the magnetic field is uniform. Now, when you're on a roller coaster, and I have the analogies listed out for you right here so we can remember them. So when you're on a roller coaster, if you're sitting, say, at the top of the hill, you may feel slight wind, maybe just the wind for the day. But as you're going down and even at the bottom, you feel much more wind. You feel more magnetic field. Remember, the wind's analogous to the magnetic field, which is also called B field. Flux is the measurement of magnetic field. So in this case, it would be the measurement of how much wind. So if we wanted to measure the amount of wind here versus the amount of wind here, they would be much different, right? So it's safe to say that the flux at point 1 would be much less than the flux at point 2 because there's much more magnetic field, more wind at point 2. Flux depends on the density of the flow. So in the instance of our roller coaster, the velocity, how much wind is going. It varies by the boundary facing the direction of the flow. So if you're measuring an area at an angle, not as much wind may be able to get through. Flux is proportional to the area. So if we were to only measure 0.1, but then we were to, say, measure all of 0.3, we might have a larger flux because we have a larger area. Okay, now how does this all correlate? So let's try out a problem. It says, in the configurations below, determine the direction of the current, which is I, the movement of the people, from left to right, 0, or from right to left through the resistor R, the middle coil. So remember, the points are the resistors, right? So it's asking, what is the current? In part A, it says when the coil on the right with the battery, we know this is the battery because it has the two lines right there denoting positive and negative. So what is when the coil on the right with the battery moves to the left towards the coil with the resistor? Okay, so to answer this problem, let's first just focus on this circuit alone. This circuit alone, if you were to use your right hand rule, your B field should be pointing outward this way. That should be your B field. Because if you take your thumb, the only way for your thumb to be able to wrap around and follow the current, right? Because the current is traveling like such. It'll wrap around, come back down, wrap around, come back down. Your fingertips will be pointing outwards towards your right. That means the force is also running around with the current. So for this specific problem, we will say that if we were to label this as 1 and this is 2, for 1, the B field is to the right. For 2, 2's B field depends on 1. So as 1 moves this way, its B field starts acting on 2, right? Because it's entering its B field. Well, when we're changing, so 2 would already have its own B field because it's already have a circuit running through it. When 2 B fields meet, you're alternating the B field. You're creating a flux, right? Because flux is the measurement of magnetic field passing through, so the change of a magnetic field. However, circuits, just like anything else in the world, like homeostasis. They don't like change. So when this circuit moves in, its B field is now acting. So this circuit 2 will compensate for circuit 1's B field, which is originally acting this way. It will go in the opposite direction to try to balance things out. So now we know that circuit 2's B field will go this way to counteract against the flux caused by circuit 1 coming in. Now that we know circuit 2's B field is going out, we can trace with our right hand rule. Our fingertips should be pointing to our left. Our thumb wraps around. We follow the wire with our hand, and we know that the circuit or the current is going up, down, so it's going from Q to P. So we know that it's from right to left, going from Q all the way around to P. Now when we look at the part B, when the switch is open and was kept closed just prior to that. So now that we know how flux works and how magnetic fields don't like the idea of flux, they don't like change. Although the switch was just opened, it still has a current running through it for quite some time, right? It doesn't just automatically lose its circuit. So in that instance, right when the switch is open, there is still a circuit, meaning there is still a magnetic field. So when we explain this one up here, we knew that the B field was going to the right. It's the same exact battery. So this one will also be going to the right. This one's B field. Its current also positive to negative, remember, so its current's also running this way, follows the loops down. Now if we were to move this one closer to this left one, the exact same thing would happen. This one's B field, which is originally going left, or would change to go left because of number 1's B field imposing on number 2's B field. That would create a flux. Like we said, things don't like change. So circuit 2 is trying to compensate for that change by changing its direction of B field, going the opposite way. So our answer is C again, right to left.